So section 7.3, we really hit that first objective yesterday, which really it's learning the basics of logarithms. And if you use that snail shell thinking, that circular thinking, then eventually you'll be able to look at these and say, oh, I understand how this works now. But we need to graph today. So graphing. You guys have always been good at graphing, so hopefully this will go really well. So that's our major objective for the day, is to graph these correctly. So there's where we're at. Now, we have to remember back, and I know it's been a while since we did 7.1 and 7.2. A few of you did last Friday's assignments, so it's fresher in your head than everybody else's. But when we graphed our exponential growth and exponential decay, we got this red graph right here for something like y equals 10 to the x. Now, because our number system is a base 10 system, we like to look at that one first and say, you know what, if this is what it looks like, and we're working on its inverse, which is logarithms, then what should happen is we should see a reflection through the line y equals x. And that's what's happening here. Here's 10 to the x, and here is logarithm base 10 right here. It flips it over. But more importantly than that is that when we covered exponential decay and exponential growth, those never crossed the x-axis. So if we're talking about logarithms as an inverse, they're never going to cross the y-axis. It's not going to happen unless there's a translation involved there. So, A, logarithmic function, as you write that in, I'll go mark the tardies for breakfast. A logarithmic function is our inverse to exponential growth. So logarithmic function, inverse of the exponential function. The graph shows y equals 10 to the x, and of course its inverse, y equals logarithm of x. Remember, if it doesn't say the base and it's log, it's base 10, our base 10 number system. So note that 0, 1, and 1, 10 are on the graph for 10 to the x. 0, 1, 1, 10. Then it says, note that 1, 0 and 10, 1 are on the graph of y equals logarithm of x. So you switch them. And we know that. We know the first step to finding any inverse is switching the x's and the y's. The domain becomes the range, and the range becomes the domain. So recall that the graphs of inverse functions are reflections of each other across the line y equals x. We can graph y equals logarithm base b of x as the inverse of y equals b to the x. Now, it's not going to be as difficult as, it first looks when you're going through this, because I know we freak a little when we see logarithms, but they're not that bad. And the reason they're not that bad is because logarithms are as pure of an example that we have of inverses in mathematics. When the bases match, they disappear. It's just like magic. So, what is the graph of y equals the logarithm base 3 of x? Describe the domain, range, identify the y-intercept, and the asymptote. Well, we start here. And we say, I don't know what that graph looks like. It's got to look something like that logarithm graph they had up there before, but whenever we start graphing anything, we're supposed to make tables. So how do I do that? Well, we snail shell it. Logarithms don't make any sense to us right now, so what we're going to do is translate this into exponential form by 3 to the y equals x. And you notice something very strange has happened here. We're not going to put numbers in for x anymore. We're going to be putting numbers in for y. Remember before when I said this is as perfect an example of inverses as we can get, and the domain and the range are supposed to swap? They literally swap everything with logarithms. So when we make our table where we would normally put in x values, we don't do that anymore. We're going to put in y values. Now, we don't want to use negatives because, again, We're hoping that we're just going to see something really nice out of this graph. So let's just try 0, 1, and 2 and see what happens. What's anything to the 0 power? 3 to the first? 3 squared? But we don't graph it backwards. That happens sometimes. People get the whole backwards thinking going. We don't graph it backwards. We graph it as 1, 0, 3, 1. So 1, 0, 3, 1, 9, 2. And then I remember with exponential growth was the x-axis we never crossed. With logarithms, which are their inverses, it's the y-axis we're never going to cross. So it's going to do this. Now, if you're thinking, well, I'd really like something in the table to show me this. Well, to do that, you have to use fractions. And typically, we don't like using fractions in a table. When we make our table, we like to pick the numbers, and we like them to be nice and easy. So we just need to know that that's where the asymptote is going to be, the y-axis. So let's draw it on there. So in your notes later, you'll say, oh, yeah, that's why we did that. We've got an asymptote there. And there is the line x equals 0. So now we'll have questions like domain and range and all that good stuff. Well, the domain, the x is right here at 0, but we can't use 0. Remember, it's never going to get there. That's an asymptote. We need everything to the right of that. So x is greater than 0. Now range is about up and down. And granted, I mean, you look at this and you think, well, it's not going up a lot, but is it going up? So eventually, it'll get to all of the y's. And this pretty obviously is still going down. So it's actually going to be all real numbers for the range. And again, if you think back to what we did in 7.1 and 7.2 for exponential growth and decay, the x's were all reals, and the y's had restrictions on them. So it's totally flipped. Y-intercept. Does this ever cross the y-axis? We're going to write none. It did have a vertical asymptote, and that vertical asymptote is at x equals 0. So reflection through the line y equals x creates this nice little logarithm graph. Again, what we have to get used to is we put in the y's this time, and the x's come back from the formula. Alrighty, they changed the number on us. This one says y equals logarithm base 4 of x. Now, I'm right-handed. I snail shell as a right-handed person, so I'm going to rewrite that as logarithm base 4 of x equals y. Again, we've got to graph it, and then we'll talk about domain, range, x-intercept, asymptotes, all that good stuff. Snail shell it for me. What's it going to say? Some good numbers to put in for y. Now, we're not going to graph 16.2 because our numbers are from -10 to 10 here, but at least it gives us something to aim at. So we've got the 1, 0, 4, 1, and something to aim at out here. But here's the key. We have to know that's not going to cross. Not going to cross that y-axis. Why not? What's the y-axis now? It is. Now, before we go to the next ones, we're going to start with translations and those types of things. The only time we're going to have to change that is if this thing is moved right or left, because that's going to change our asymptote to x equals whatever it is. Which of our letters, A, H, or K, deals with shifting things right and left? So H is going to be what's responsible for us having to move that asymptote. All right, let's get the rest of this filled in. Domain. Yep. Can't use 0. It's an asymptote. In fact, let's put that down. Range. Up and down forever. Y-intercept. Exactly. We don't get one. Now, why do we harp on that so much? I mean, why is there even a spot for y-intercept there? Because when we get to the test, some people try to use their calculators for this. And the calculator does the best it can, but it doesn't know any better. So when you see it, it looks like the graph stops right here on a graphing calculator. We have to know it doesn't stop. It keeps going. It never touches the y-axis, but it keeps going forever. So it's called graphing calculator error. It's doing the best it can. It just cannot graph this completely and thoroughly. All right. And you don't need a graphing. See how you don't need a graphing calculator for these anyway? You just snail shell and it's a piece of cake. All right, so the function y equals logarithm base b of x is the parent for the function family. And it's a base b that they have here. They're leaving it wide open. And we can graph. Here's where h and k come in. Y equals logarithm base b of the quantity x minus h plus k by leaving h and k off to start with. We're going to make our nice little table like we always do, and then we'll go ahead and move it to h and k units. So we'll translate the graph of the parent function, h units horizontally, k units vertically. And the a in front of this whole thing is still the a that we've always known. If it's a number that's bigger than 1, we've got a vertical stretch. Fraction between 0 and 1, a compression. Could have a reflection if there's a negative in front of it. The question is, when do you use that? You know, because I'm really liking that this doesn't have an A in the front. That's going to be really easy. Well, when we get to that one, you'll see it's also not very hard. So here we go with our big chart of this is how we're going to do this. So parent function doesn't have the h and k in there. John, head up. Taking notes, paying attention. If our a value is greater than 1, don't look at the negative. We know that's responsible for reflections. Then we have a stretch. If it's between 0 and 1, then we're talking about a compression. And this is vertical, so it's squishing. And then a reflection if we do see the negative. Translations, still left and right for h. X is still the naughty variable. It's going to look like the opposite of what we need. K is still in the back doing the up and down. Putting it all together, there is y equals a, logarithm base b, x minus h plus k. So lots going on. All right. How does the graph of y equals logarithm base 4 of x minus 3 plus 4 compare to the graph of the parent function? Well, the first thing we have to do is figure out what the parent function is. And the parent function has always been leave off h and k. Take everything else, and that's your parent function. So our parent function is y equals logarithm base 4 of x. And if you're thinking that seems familiar, well, that's the graph we just did a little bit ago. So we'd snail shell this. Like I said, I'm a right-handed person. So I'd snail shell this way and make my little table. Like so. But this has to be moved. We got to move it h and k. So we have to figure out how is this. Oh, they used a b for base. Going to need to be moved. So can you tell me, where will this go? Yeah. Now, just like before, if we're going to graph something effectively, we want to put the vertical asymptotes on this thing right away. It's not 0 anymore. This thing moved horizontally. So our new asymptote, you said we're going to move it 3 to the right? It's x equals 3. Let's get it on there. Now, just like we did before, we want to make a dashed or dotted parent function, and then we're going to move it so that that asymptote makes sense. So we're going to put our 1, 0 and our 4, 1 on here. And aim kind of at that 16, 2 piece. So we only really have to move 2 points to get this graph effectively. We're going to move those 2 little points, 3 to the right and 4 up. And that's our 1, 0 and our 4, 1. And there is our new asymptote. We already know it's pretty flat, you know, up at the top there. It's very, very flat. But there it is. So that changing horizontally for our h, this time it has affected the domain. What's our new cutoff? Can it be 3? No, that's an asymptote. So it's going to be x is greater than 3. Did it change the range to have that 4 in the back? Still going up and down forever, isn't it? So all reals. So even with an h and k in there, not the most challenging graphs in the world, you know. We have our little table with just a couple of numbers in there. If we remember, we put in the y's, we should be okay. These two. How does the graph of each function compare to the graph of the parent function? Well, let's talk about that one right away. So take a look at this one. Oh, this is kind of silly. What's the only change from this one and the last one we just did? Yeah, I wish they would have done something a little bit creative here, but we're still going right 3 and up 4. Maybe they were hoping that we would miss that the base changed. I don't know. So now our parent is going to be logarithm base 2 of x equals y. When you snail shell it, what is it going to say? 2 to the y equals x. Now it's a small number, so we can probably do at least one more number than we did before. 0, 1, 2, 3. Let's see if we can fit them all on there. Anything to the 0 power is 2 to the first, 2 squared, 2 to the third. Yeah, all of those will fit on there nicely. But let's put our new asymptote on there so we don't forget. Where's the new asymptote going to be? Yeah, x equals 3. Sometimes we get busy and we forget we've got all these moving things we have to do. So this one was 1, 0, 2, 1, 4, 2, and 8, 3. So it's going up a little faster than our 4 was, our base of 4. And we know where to move it. So you can take those 4 nice points and move those 3 to the right and up 4. Again, once we have that table, then it's just counting. So, new domain? Yep. Range? So now we get to the interesting one. That a value for that b over there, y equals 5 logarithm base 2 of x, that's not a 1 anymore. What is that going to do to this graph? It will. So if we took our graph, which is in fact this one right here, 2 to the y equals x, if we took this black graph right here and we vertically stretch it, does that change the asymptote? No. So we just have to figure out how all that's going to come together. So let's see. This would be parent function, y equals logarithm base 2 of x, so we'd still do 2 to the y equals x. We would still get this exact same table. So, sorry I'm going through that kind of fast, but does everybody see that the base is exactly the same as the problem we just did? Yeah. So now I have to think, well, what do I do with the 5? I mean, isn't everything supposed to be backwards? To a point. When I asked what the 5 was going to do, you said it was a vertical stretch, right? So does a vertical stretch affect the x's or does it affect the y's? So we're going to multiply all those y's by 5. We'll just make a third little column here and multiply all of those y values by 5. And we're not going to be able to graph them all, but at least we've showed we know that, hey, vertical stretches still affect the y's. Those are the verticals. So we're not actually going to graph the middle column here. And because a vertical stretch does not affect the asymptote, it's still right here at the y-axis. And I'll just go ahead and graph 1, 0, 2, 5, and 4, 10. And yeah, that's quite a stretch. So not a whole lot of curve on our little negative 10 to 10 there. What's the domain? Yep, x is greater than 0. As we said, stretching it out does not affect the domain. And what's the range? Exactly. I mean, it's more obvious now because this is so much more straight up and down than the other ones were. But there it is. Hey, we just learned how to graph logarithms. Is it tough? No. Graphing. I shall sanitize my hands and get you some graph paper here. All right. Now, again, it looks longer because of the instructions there. Like I said, graph them and give the domain and range. I'm not going to bother. Okay, everybody, what's the y-intercept for our graphs that don't go right and left, up and down? It doesn't get one. Remember, it's never going to cross.